All right, this will be the final question in this exam hack series for mechanics. Final video, and we finished analyzing the paper, covering everything, every possible question they can ask, every style, and if they do add content or new styles, I'll add to this playlist, but it's unlikely because they haven't really changed anything from what I've presented here in a good part of a decade. So it's a pretty good bet here. And so this will be valuable and valid for many years, what I've made in this series. Why I spent so long on it. Okay, so this final question is called the incline-pulley question. I've left it to last because it's usually worth a lot of marks and it incorporates a lot of different things. We need no extra theory here, and so we're going to just jump into questions. But it looks like this. It's basically a scenario where you have inclined planes and pulleys, and you have to make calculations from that. You can see they all look very similar. And so got all those there from as far back as 2017, and I've answered all the odd ones and extracted answers for the even ones. I thought that was sufficient. It's 50 pages long. It's a massive worksheet. So download that and you should be good for this question. But we're going to go through two types here in this video. So let's just jump into it. Let's have a goddamn good time. Okay, so like I said, the reason I've left this to last because it incorporates a lot of things in there. If it does come up, it comes up at the end of the paper and it's worth a lot of marks. As you can see here, like this first one that we're about to do is worth 12 marks in total. It's a lot of marks. Yeah. We'll see, it's not that difficult. It's not that scary, baby. Okay, so we've got this diagram. So I'm going to start redrawing the diagram. This diagram here looks like this. And so we'll call this theta 1, theta 2. We got the pulley at the top here. We got our mass A here. Runs over this pulley and our mass here. Just doing a rough sketch like I've done for all of these things. This is our mass A, mass B. And B. Okay, so our theta 1 is 30 degrees. Our theta 2 is 60 degrees. We have the mass of A equals to 1.2. Oh no, that's the mass of B. 0.8 kilograms. Mass of B equals to 1.2 kilograms. Okay, and then we should identify what we've got. The weight of A. Our incline, we know that will be theta 1 here. And the weight of B. This will be, this angle here will be our theta 2. We'll have the tensions acting in, right? It's one string, as you saw in the pulley question and in the connected particle question. And the tension will be acting inwards here. Okay, so this is just explaining this situation. They both start at rest and the strings are taut. Okay, so given that both the planes are smooth, so there's no frictional force on either of these planes, find the acceleration of A and the tension in the string. Well, we've seen this before many times, but it's just a more difficult scenario. So we want to resolve the forces about A and resolve the forces about B, and then we can find the tension and the acceleration. And it's important to note that, well, this thing here, B, weighs more, has a greater mass than A, and is at a higher incline. So the acceleration of the system will be this way, right? So it will have more force going on this side of the pulley than that side, due to the incline and the weight, mass. Okay, so the sum of the forces about A is going to equal to the mass of A, the acceleration of the system. What are the sum of the forces about A? Well, it's accelerating in this direction, so it's going to be tension minus the weight down the slope, which will be WA sine theta 1 equals mass of A times A. Take that over. We get an equation for the tension plus WA, because I know I'm going to have to substitute one into the other. Okay, we'll call that equation 1. The sum of the forces about particle B is going to equal to the mass of B times the acceleration of the system, or the acceleration of B. So this is just going to equal to, now this B will be moving down, so it'll be the weight of B down the slope, sine theta 2, which is just this part here, minus the tension, equals to the mass of B. So I guess let's rearrange this for T as well, so let's easily sub them into each other. Get T equals to, take that over, we get WB sine theta 2 that MB A. That equation 2. So we sub equation 1 to equation 2. We'll get MAA plus WA sine theta 1 equals to WB sine theta 2 minus. Okay, we got to rearrange for A, so therefore we get mass of A times A plus mass of B times A equals to WB sine. So I'm keeping it all in general form, which is how I like to do it. You can sub it in values in earlier, but I like to keep it all in general form and then sub in at the end, as I've done throughout the series. Minus WA sine of theta 1. Therefore we get, if we factor out an A here, we get MA plus MB equals to WB sine of theta 2 minus WA sine of theta 1. We have all of these values, so therefore we can find A. So therefore A, B, well, the mass of A is 0.8 and the mass of B, so these added together will just be 2. 2 equals to, the weight of B will be 10 times this, which is 12. 12 sine theta 2 was 60 degrees. The weight of A will be 8, 10 times this. Sine and theta 1 was 30 degrees. Cool. So therefore we get 2 times A equals to 12. What is this? Sine of 60 is square root 3 over 2. Square root 3 over 2 minus 8. Sine of 30 is a half. Check that. Okay, so we get that 2A equals to 6 square root 3 minus 4. So this equals to 6 times square root 3 minus 4 2. It's 3.16. Round that, so this is 3.196 ... meters per second squared. So if we round that, we get the acceleration of the system and both the particles individually. So the acceleration of particle A, 3.20 squared. And then simply to find the tension, we just substitute back into one of those equations. So let's say we'll substitute into 1. Tension will be MA times A. MA was 0.8, right? Yep, so 0.8 times 3.196. You want to be careful about the rounding. Plus or minus? Plus WA sine theta 1. WA will be just 8 times sine theta 1 is 30 degrees. So that's a half. So therefore the tension, this will equal to this times 0.8 plus 4. It'll be 6.556. So therefore, if we round that, we say 6.56 newtons. That's the tension in the string and the acceleration of particle A, which is also the acceleration of particle B and the acceleration of the system overall. Cool. It is given that instead both the planes are now rough with the same coefficient friction mu. for both the particles. Find the value of mu for which the system is at limiting equilibrium. Okay, so when it's at limiting equilibrium, the system is about just on the verge of starting to move in the direction it would naturally move. In this case, would be this way. So if it's just about to move, well, we need to introduce this frictional force and be aware of what direction it will take for each particle, because it'll be different. As the system is just about to start moving, A will just about to start moving up, and B will just about to start moving down. So that means that the frictional force, let's say I call it F mu A, on A will be acting this way, right? Because this is just about to start moving up, and the frictional force on B, just to start moving down, will be this way. So F mu B. Okay, and the acceleration of the system overall will be 0, right? It's not moving. So if we want to find mu, this is II, we want to find mu, well, we can say the sum of the forces, so we need to set up an equation for mu. The sum of forces about A is just going to equal to 0, right? Because the system is not moving, A is not moving. And what are the sum of the forces about A? This would be the tension minus the frictional force and the weight down the slope. This will be the tension minus frictional force of A on A minus the weight down the slope, which is WA sine theta 1 equals 0. So therefore, we can rearrange for the tension like we did before. F mu A plus WA sine of theta 1. And for the sum of the forces about B, because we want to get rid of this tension, so we have an equation just for mu. Sum of the forces about B, well, this will be equal to the weight down the slope minus the frictional force minus the tension due to its direction. This equals 0, so it'd be the weight down the slope, which is that, minus the frictional force reacting up the slope of B minus the tension, which equals 0. So we can take that over and say T will equal to WB sine theta 2 minus F mu B. For that 2, for that 1, we substitute 1 into 2. We'll have an equation just because this will be involving mu, just involving mu, and then we can find mu for when it's at limiting equilibrium. So that's just putting one of these into the other. So we get, this would be F mu A plus WA sine theta, sine of theta 1 equals to WB, sorry, just had a mind blank, minus FB. Okay, let's take this over. We get F mu A plus F mu B equals to WB 2 minus WA theta. Okay, so let's just start this. We're going to want to solve this equation, but let's find what these things are first. So F of mu A is just mu times the reactional force on A. The reactional force on A will just be this component of the weight, which is WA cos theta 1. I have videos on all of this, that's why I'm not explaining that in detail. WA cos of theta 1 for F mu B. So it'd be mu R of B, which would be mu times WB theta 2. So therefore we get the star equation becomes mu WA theta 1 plus, subbing these in, mu WB theta 2 equals to WB sine of theta 2 minus WA sine of theta 1. Factor out a mu here. Get this. Yeah, just factor out a mu, and then we can divide through this. I want to just sub it in here, it's fine. So we get mu equals to, well, WA is 8, cos theta 1 is 30 degrees, plus WB is 12, 1.2 times 10, cos of 60 degrees, equals to WB is 12, sine 60 degrees, minus 8 sine of 30 degrees. Okay, so therefore we get mu 8 cos of 30 over 2. Yep, so 8 square root 3 over 2 plus 12. This is a half. Yep. Equals to 12 times square root 3 over 2. This is square root 3 over 2 minus 8 half. Okay, so therefore we get mu equals to 4 square root 3 plus 6 equals to 6 square root 3 minus 4. So therefore mu equals to 6 square root 3 minus 4 divided by 4 square root 3 plus 6. Plug that into your calculator. You get your value for this coefficient of friction. Root 3 plus 6. 0.94. 0.49. 0.494. So mu for this limiting equilibrium is this. Okay, so you can see there's quite a lot going on, but there's no extra theory that you need here. 6 marks. So the important thing there was to note the direction of the friction, because it's just about to be moving this way, going clockwise. Frictions act accordingly. Okay, and I thought I'd do another one. It's the same sort of scenario, but in this case you have to work out different. So, and this kind of one pops up a lot as well, so I'll just do this as well. It's 8 marks. Okay, so we want to redraw this. This is theta, pulley, A. Better. This is our A. This is our B. Our B. The mass of B is 3 kgs. The mass of A is 2 kgs. This is at a distance, we'll call it D. D is 0.45 meters. And theta is 18 degrees. Okay, should note that the tensions will be acting in again. This, we have the weight of A here, we have the weight of B. Yeah, that's theta. Okay, so it's smooth, fixed plane, so we don't have to worry about friction. The string passes over a smooth pulley at the top plane. The particle A hangs vertically above. So just explaining this diagram, the system is released from rest with the string is taut. When A reaches the ground, the string breaks. So A moves this distance D to the ground, the string will break, and then B will be in free motion. So find the total distance traveled by B before coming to instantaneous rest. You may assume that B does not reach the pulley. Okay, so instantaneous rest, that means this is the point at which the velocity of B is 0 at the top of its motion of the slope. So when it's at the top of its motion of the slope, its velocity will be 0, so it'll be instantaneously at rest. To find the distance it travels to get to that point, we have to split this up into 2 stages. To be the stage where B is being affected by the string and the weight of A, so A is being pulled down. So for the first stage, we'll say stage 1 of its motion. So this is when B is being affected by the string. It travels, okay, well, I guess first thing we're going to really need to do here is find the acceleration of the system, right? Because we're going to need that to calculate these distances. but I just wanted to explain. So in the first stage, B is affected by the string, right, and the weight of A. When A drops to the ground, then B, and the string breaks, and then B is in free motion, so it's no longer affected by the string. So we need to kind of treat them in two different stages, because there's sort of different things acting on B in both of those stages. But we need to find the acceleration of the system to start with. How do we do that? Well, we do sum of the forces about A. So we're find acceleration of system, which is, you know, of B. So the sum of the forces about B is going to equal to the mass of B times the acceleration. Sum of the forces about A is going to equal to the mass of A times the acceleration. Forces about A be WA minus T. WA minus T equals MA. We rearrange for T. We get WA minus MAA. That's equation 2. And for FB, we have tension minus the weight of B down the slope. That 1. We'll substitute 2 into 1. Find the acceleration of the system. This goes into here. We get WA minus MAA. It's WB sine theta equals to MBA. Take that over. We'll get MBA plus MAA equals to WA minus, I just took this over, minus WB sine theta. Therefore, our A will be equal to, factor this out, A minus WB, and we have all these things, so we can find A. So it'd be A, mass of B is 3 and 2, so this will just be 5, 3 plus 2 equals the weight of A is 20, and the weight of B is 30. It's a sine of theta, which was 18 degrees, I'm pretty sure. Yeah. Okay, so A will equal to this divided by 5. Therefore, A equals 2. These are quite long, but I think they're that, maybe they are a little difficult. They're pretty difficult. Not even done yet. So 2.14. So keep it 2.145. Is the second squared. This is an important value. This is our acceleration of the system. Okay, so now we have the acceleration of the system, we can start calculating these distances. So for stage 1, as I was trying to explain before, you know, of its motion, this is when B is traveling towards the ground and hits the ground. So in this part, our B from its starting position, you know, will travel up the slope. This is, you know, it'll travel up to here. This is when B has hit the ground, and this distance that it travels from its, you know, its starting point to its ending point here, this distance is 0.45 meters, right? So if it pulls it down 0.45 meters, well, then in the stage 1 it's moved up 0.45 meters. So our first distance for stage 1 is 0.45 meters, right? And then at this point, it'll snap. And so we want to find the velocity here. Final velocity here, because if we find that, then we can find the distance for stage 2 when it's in free flow, free motion. So let's find the velocity at the end of stage 1 here when the string snaps. So the velocity here, we have the displacement, which is S. So S is our 0.45 meters of this particle. It's accelerating up the slope at this, right? at its initial velocity, because they both start at rest, is 0 meters per second. So v squared equals u squared plus 2as equals 0 squared plus 2 times 2.1459 0.45. So therefore we get this 2 times 0.45 2 is 1.9313 ... So therefore v at the end of stage 1, so just when when the string snaps, the velocity of b will be this 0.3. I'm not rounding too much because these aren't numbers they're not our answers, but we're going to have to use them. Okay, so that's the speed at the end. So for stage 2, so now b is in free motion up the slope. So this thing b now, so the string is snapped now, so it's just in free motion and it's moving at a speed of this, so initial speed of 1.387 ... second. The acceleration down the slope we don't know, but we can find that pretty easily. And the final velocity, the distance we want, is this distance, right? v2, right? Where the final velocity at the top, 0, right? Because that's when it comes to instantaneous rest. And the acceleration down the slope is just going to be minus g sine theta, right? This is the acceleration, g down, this is theta. The acceleration down the slope is just, and this just comes from, I guess if you want to be super clear, this comes from, the forces acting upon particle B is going to equal to the mass of B times the acceleration of B. And the forces acting on particle B, now it's in free motion, is just the force, the weight due to B down the slope. So it's just minus mb g sine theta equals mba. That cancels with that, and you get exactly what I have here. So therefore a equals to minus 10 sine of 18 degrees. So I might just keep it like that. I can substitute it in. So now this distance, which we want to find, so we know that v squared equals u squared plus 2as. So v squared is 0 squared at the top of the slope. Our u will be this. Squared was this, so 1.9313. I'll just plug this in. 1.3897 squared plus 2 times minus 10 sine degrees d2, our distance that we want to find. So we rearrange for d2 and we get this squared and divided by 2 times 20 sine 18. You get 0.312 meters. Okay, so we have the distance in stage 1, which was 0.5 meters, the distance in stage 2 after the string is broken to the point where it's at instantaneously at rest. So then we can find the total distance traveled by b until it comes to instantaneous rest. So the d total will simply be d1 plus d2 equals to 0.45 plus 0.312. So therefore d2 equals to this 0.762. Okay, meters. And that's 2 really good examples. All of the examples in here, all of the questions are pretty similar to that. Occasionally they work in energy. Other than that, we're all pretty much like that. And you have them all there with written and extracted answers for you. That's it. I hope that was useful. And now to sum up this series as we're finishing it, I'm going to discuss the 2 main things that I was trying to get across when I was kind of openly talking at the end of these videos. Well, now we have come to the end of the series. I've been doing these ending sort of monologues and discussions, an open flow of thoughts to inspire and intrigue you. But I have had really some main points which I've been trying to get across here, and I'm going to outline those two. There's two of them here. So as we've come to the end, so I'll just do an overview of the points, the 2 points, main points I was trying to get across, other than just, chatting and flowing and talking. So the 2 main points were this. Number 1, nature is intelligent. It's not a mundane and stupid thing. It's intelligent, and we should live in accordance with it. You can learn from it, and if you feel lost, confused, well, confront nature. I'm talking about physical nature. You can learn things from the physical world. Observe the physical world, and it will teach you lessons. And in fact, I will say that you can learn a hell of a lot more from the physical world than you can the digital one. It's an intelligent thing, and it has things to teach you, and it wants to help you. And so yeah, that's number 1. Number 2 is asking questions. When you ask powerful questions about knowledge or content that you find, then you will learn deeper, and you will learn better, and you will expand your knowledge and understanding. This goes for education and also for life. I'm trying to show you the power of asking high quality questions. If something is presented to you which seems obvious or seems just this is it, this is how it is, it's not obvious, and it took genius people to discover it. It's only obvious now after the fact that we found it. And so you should ask and question these obvious things, especially in subjects like science and math. Question the things that seem obvious, and that will have a great benefit for you in your life, your education. So those are the 2 main points, and they're very powerful ideas. If you use them and implement them, they will transform your entire life, and I really do believe that. So that's it. I want to say that I've actually thoroughly enjoyed making this series. Sometimes I can't always say that, but I have thoroughly enjoyed making this series, and I hope you found it useful and maybe thoroughly enjoyed watching it. Yeah, that's it, and peace and love.